So some of you may have clicked on this video because you saw the title. Well, I'm sorry to announce that this is an educational video and calculus puns are not integral to learning. For those of you who don't like puns, here's a warning that there will be one or two more sprinkled throughout the video. Okay, let's just begin because I feel like some of you are at the limit of your patience with me. It's too early to get up. Time to grab myself a nice cup of coffee. It'd be great to know how much one of these small cups of coffee will help with my tiredness. To do that, I need to know how much coffee this cup can hold. I find that a coffee cup can be represented by the equation y equals x to the 6th power. Let's assume that the units are in centimeters. Not bad, right? Here are the equations if you want to graph your own cup of coffee. We can rotate this graph sideways for easier math. Now let's get into the math. We can use a disk method to find the area since there's no hole in the middle. First, we'll plug the radius into the integral. The exponents multiply and simplify this equation a bit more. Then, we take the antiderivative, which is 3/4 times x to the 4/3, and plug in the values for the bounds. Finally, we simplify the equation a bit. This answer is perfectly acceptable on an FRQ, but I'll go one step further. Our volume of the cup turns out to be about 5.94 cubic centimeters. That means that this cup can hold 5.94 milliliters of liquid, since 1 cubic centimeter is equal to 1 milliliter. Not a whole lot, but I probably shouldn't be drinking too much coffee anyway. I guess you could say that the result was quite disappointing. Okay, it's 8 o'clock now, and it's probably a good time to plan out my day. It's better to have breaks between working sessions to maximize efficiency and to avoid getting tired. I find that my efficiency in completing tasks is related to how often I take a break through the equation y equals negative 2t cubed plus 4t squared minus t plus 4 for time t between 0 and 2. How often should I take a break to maximize efficiency? Okay, first we need to know what we are doing. We are trying to find the absolute maximum of the function. Recall that, to find the absolute maximum, we create a table with our endpoints and all critical points. Then, we choose the point in our table with the largest value. Let's start by finding the critical points. First, we'll take the derivative of the function. Next, we'll set the derivative of the function equal to 0. Now we'll find the zeros by plugging the values into the quadratic equation. We'll use a calculator on this step just to make things easier later. We get two solutions, which means that there are two critical points. Now let's put the numbers into an xy table. We'll also add the numbers 0 and 2 to the table since they are the endpoints. For every value in the xy table, we'll calculate the y value from the original function. Now, we simply choose the largest value since we are trying to find the absolute maximum. Since the x values here represent how often I take a break, the optimal interval to take a break is at every 1.19 hours. I just finished a DBA for an online class. For those of you who don't know, a DBA is a phone call to your online teacher where they ask you some questions related to the class. Anyways, I don't know if it's just me, but I always get really nervous that I'll forget something during the call, and so I pace around a lot. My distance in kilometers with respect to time in minutes can be modeled by the equation v of t equals t to the 8th minus 4t to the 6th plus 4t to the 4th minus t squared plus 0.05. At time t equals 0, I start the DBA and I end the DBA at time t equals 1.7. Assume that I pace back and forth in a straight line. There will be 3 subparts to this question to mimic the feel of an official AP exam. We'll use a calculator on some parts of this problem, but I'll still try to show the steps as much as possible. First off, what is my average velocity on the interval 0 to 1? Average value can be found by integral over interval. We'll do this integral by hand since it's quite simple. We'll also plug in the interval. Our bounds are from 0 to 1. Now we'll evaluate the integral. Then, we'll also divide by the interval and plug in numbers for the bounds. You can verify that the equation just cancels out when you plug in 0 for the lower bound. This answer is perfectly sufficient for an FRQ on an AP exam, and it's probably best to leave it as is without simplifying to avoid making mistakes, but I'll simplify in this case. Since the denominator is 1, we can just leave that out. We'll also convert 0.05 to a fraction to make our lives easier. And the numbers are a bit ugly. Actually, I take that back. The numbers are very ugly, but here we have our answer. 71 over 1,260, or about 0.056 kilometers per minute. For the curious, that's about 3.3 kilometers per hour. Alright, now for the second part. At time t equals 0.5, am I speeding up or slowing down? Recall that speeding up is when velocity and acceleration are the same sign, and that slowing down is when velocity and acceleration are of opposite signs. The equation for velocity is given in the problem, so all we'll need to do is find the equation for acceleration, which we can do by taking the derivative of the equation for velocity. And that's the derivative. Pretty standard stuff. We just used the power rule a couple of times here. Now let's plug 1/2 in for t to check if the acceleration is positive or negative. I've converted everything to fractions to make the math easier. You'll see why in a moment. Let's evaluate the exponents first so that it'll simplify. And now, if we simplify the fractions, we can see that the acceleration will be positive. We'll also do the same for velocity. We plug 1/2 into the velocity equation and convert it to a fraction for easy math. Next, we'll evaluate the exponentials. Then, let's simplify the fractions. The 1/4s cancel out, and if you add the remaining fractions, you get negative 11 over 1,280, which is negative. Finally, we compare the acceleration and velocity values. Since acceleration is positive and velocity is negative, in other words, they are of opposite signs, I must be slowing down at time t equals 0.5. Last part for this question. How far have I traveled by the time I end this call? Because we're finding distance traveled as opposed to displacement, we'll need to integrate the absolute value of my velocity. Remember that I end the call at t equals 1.7. We'll set up the integral with the bounds 0 and 1.7. To make things a lot easier, we'll be evaluating the integral on a calculator. Okay, now let me get my calculator out real quick. Oh, I can't do calculus on that. I need an actual calculator. There we go, much better. Here's how I key this equation into my old TI-83. This varies across different calculators, and it's very possible that yours is different. You'll want to use the definite integral function and put in 0 as the lower bound and 1.7 as the upper bound. Again, the specific process may be different depending on your calculator, manufacturer, and model. After doing all this, I find that I've traveled a total of about 0.87 kilometers. This answer seems within reason if you think back to the original problem. Shown here is a graph of h of t, the derivative of my happiness levels over time t in hours today. At time t equals 0, or 6 a.m., my happiness level is 0. If my happiness level is greater than 0, then I am happy. If it is equal to 0, then my emotions are neutral, and I am unhappy if the happiness level dips below 0. There are two subparts to this question. First off, let's find the value of my happiness at time t equals 7. Am I happy, neutral, or unhappy? Okay, well, we're integrating, right? So we can count the squares. Let's see, we got 1, 2, well, those cancel out. 0, negative 1, negative 2, and 1/2, kinda? So negative 1.5? No! Please don't actually do this unless you're in a rush, or it's like a multiple choice question where the answers are spaced far apart. This is not to say that counting the squares is completely useless, and I'll show you why later. What I do to solve is split the large integral into smaller ones and calculate the areas by hand. Since they are triangles, this is pretty simple. For the quarter circle, I find the area of the entire circle using the equation a equals pi r squared and divide it by 4 since we are only taking the area of a quarter of a circle. I then add the values together to get pi over 4 minus 2, which is about negative 1.21. This means that I am unhappy at time t equals 7. Our earlier estimate that we got from counting the squares got us pretty close, which shows that counting the squares to get a rough estimate can be a good strategy. If, for example, the final answer I got was positive, then I know for a fact that I did something wrong since my answer is unreasonably off from my estimate. Next, let's find the intervals on which my happiness levels are concave down. Remember concave up and concave down? Concave down just means places where the second derivative is negative. Since the graph given here is of the derivative, think back to the problem, concave down is just where the graph is decreasing. So we look on the graph and see where the decreases happen. And there's our answer. My happiness levels are concave down from t equals 1 to 2, 4 to 5, 7 to 8, and 12 to 14. Staying happy is fundamental to having a good and healthy body. Get it? Because fundamental theorem? No one? Okay. Thank you guys so much for watching this video. Today we went over area and volume by finding the volume of a cup using the disk method, and optimization by optimizing my efficiency with respect to how long I take breaks. We also went over one-dimensional motion with my pacing around during a phone call, and the fundamental theorem of calculus with my happiness levels. This video would not be possible without the freely available media provided by all the awesome people listed in the description. More details in the description. And of course, have a great day.